And someone just asked the question, so I'll announce it. You should be able to find your zip strips now, and you should then have access to the exam form. So you can go look at the exam forms and see what you missed or what you didn't miss and go from there. So what we're going to do today is we're going to pick up this idea of action potential generation and propagation. We went a long way last time to setting up an action potential. And we invoked the three major channel types, and we're going to revisit that today and try to put them into place in the membrane. The first character in the play was the potassium leak channel. The potassium leak channels are always open. They are ungated. And the potassium leak channel is the channel type that sets the resting membrane potential. And we went through this in great detail last time, placing across the membrane these potassium leak channels, describing the disparity in the concentration of potassium such that it was about 110 millimolar inside and the cell and about 4 to 5 millimolar outside the cell. And that because of the impermeant anions in the inside, we can now set up, using these potassium leak channels, a resting membrane potential. And we spent some time last time describing the quantification of the resting membrane potential using the Nernst potential, emphasizing that the Nernst potential arose from the disparity of ion concentrations across the membrane, along with channels to carry those ions. In the initial description, we used only the potassium leak channels to generate the resting membrane potential, but then we said we could change that. We could alter the resting membrane potential by invoking a new set of channels. The new set of channels that we brought to the fore were the voltage-gated sodium channels. So these are channels that now carry a different ion species. They'll carry sodium rather than potassium. Where the concentration of potassium is always higher on the inside of the cell than the outside, the opposite is true for sodium, where there's more sodium outside the cell than inside the cell, generating a gradient such that sodium is driven into the cell both by its chemical gradient and its electrical gradient. But under normal circumstances, that sodium can't come in. The sodium is prevented from coming in because these channels, these sodium channels, are only gated by a change in charge. Under normal circumstances, they're closed. Their gates are closed. But there are mechanisms whereby we can open those channels. If we provide a little bit of positive charge, we can open those channels, swing them open, and sodium will run down its concentration gradient. Again, emphasizing the idea of the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. At rest, the dominant permeability is to potassium, but once we open the voltage-gated sodium channels, the dominant permeability is to sodium. These channels remain open only briefly, only about a millisecond, and then they inactivate. So they depolarize the membrane, but then they inactivate by having a region we'll describe today as the ball and chain moving to the open channel to effectively close or inactivate them. And we'll talk a little bit about threshold, how the threshold is the point where sodium influx equals potassium efflux. And at that point, once the threshold is exceeded, all of the ones in the neighborhood, all the sodium channels in the neighborhood will open. Yes?
Are the voltage-gated channels only positive charge sensitive, or can they be negative charge?
Are the voltage-gated channels only permeable to positive charge? In this story, yes. In reality, there's some that are anion channels. But let's not go down that road. I'll be glad to talk to you later about them. They're very cool channels, and they're found in muscle, but let's not go down that road. For our purposes here, these are all going to be cation channels. We're only dealing with cations here. And one of the important concepts that I want you to take home from this is that we can use two cations, one sodium and the other potassium, to both depolarize and repolarize the membrane. And that all has to do with the importance of when the ions come in, the change in the concentration is imperceptibly small. But that imperceptibly small change in ion concentration leads to very large changes in the voltage and the charge separation. So we'll walk our way through that. But once we've depolarized the membrane, opening the voltage-gated sodium channels, we now need to invoke another set of channels to repolarize the membrane. Where we closed last time is we described how the potassium leak channels could, over time, adequately repolarize the membrane. After all, they are a potassium permeability. The problem with that view is they're just too darn slow. You can't really use them, the potassium leak channels, to appropriately signal. It takes too long to repolarize the membrane. But it's important to recognize that what we'll do then is we're now going to invoke a new set of potassium channels. These potassium channels are voltage-gated potassium channels. So just as we use charge to open the sodium channels, we're now going to use charge, positive charge, to open the potassium channels. Once the potassium channels are opened, as long as these sodium channels are closed or inactivated, now the dominant permeability will be to potassium. Potassium flows out and repolarizes the membrane. So again, as we go through this, recognize that we hardly change the concentration disparities inside and out, but we do change the charge disparities. So we can use the charge disparities to depolarize the membrane while imperceptibly affecting the concentration gradients. Then, in the end, if there's time, we'll then think about how we're going to move these potentials. The left-hand board describes how we change the potential across the membrane, but tells us very little how we use that potential to signal over long distances. And after all, the function of the action potential is long-distance signaling in the conductal regions. So we'll lay this thinking out in 3 steps. We'll lay out an imaginary membrane where all of the voltage-gated channels are clustered at one region, but they're not distributed along the membrane. The only channel type that's distributed along the membrane are the leak channels. But now the influx of sodium will then at one point propagate a depolarization, but only for a short region before that charge is carried out across the plasma membrane through the potassium leak channels. So one of the ideas here, one of the important ideas we'll emphasize, is the potential only goes a short distance before decaying practically to nothingness. So long-distance signaling requires the dispersal of the voltage-gated channels along the membrane. And the first dispersal we'll talk about is evenly spacing the voltage-gated channels all along the membrane. We can then use the voltage-gated channels almost like a series of dominoes, opening them sequentially, allowing the sodium to come in, allowing the potassium to go out. And that will be something we'll see in unmyelinated axons. And then we'll talk about myelinated axons. You may remember we said that the maximum conduction velocity in unmyelinated axons in mammals is in the neighborhood of 1 meter per second. But in myelinated axons, we can propagate action potentials up to 110 meters per second. And we'll see now that the trick is to cluster the voltage-gated channels at nodes of Ranvier and then insulate those internodal regions with myelin so that the potentials have to hop from node to node. And we'll talk in some detail about that. But let's start here with placing the channels in the membrane. So let's just label this as placement of channels in a phospholipid bilayer. So again, let's review what we had on the board last time, because this is essential to be fluent with. And we started by invoking this purple channel, which we said was the potassium leak channel. The potassium leak channel is permeable only to potassium. And we laid out in a kind of thought experiment the concept that on the cytoplasmic side of the cell, there were these large negative anions. These are impermeant anions. And then we emphasized the idea that there would be potassium ions in the inside of the cell in the neighborhood of about 110 millimolar potassium. That on the outside, so that we said that was K in, we said K outside was in the neighborhood of about 10 now about 4 to 5 millimolar. And we emphasized here that we had a whale of a gradient where there was more potassium inside than the outside, and that typically the potassium would start to leave. But it didn't take very long for the potassium to flow down the concentration gradient before the effects of the large negatively charged anions were felt. There's now an electrostatic force on the potassium ions holding them in place. So we reach an equilibrium where the tendency of the potassium to go down the concentration gradient is exactly balanced by the effects of the large negative anions electromagnetically holding them in place. We then described, using the Nernst potential, the idea of an equilibrium potential for potassium, and we said that's EK. And we said that the equilibrium potential for potassium is normally in the neighborhood of about minus 70 millivolts. And this was said to be the resting membrane potential. And the resting membrane potential is largely determined by this balance between the large negative anions and the efflux of potassium across the membrane. And for our purposes right now, we're going to say that the resting membrane potential and the equilibrium potential for potassium are equal. We'll see in a little bit later, it ain't quite true. But for now, our purposes, we'll say the EK equals the resting membrane potential. Because this is equilibrium, it's pretty stable. So that's shown by this flat line representing the resting membrane potential being near the equilibrium potential for potassium. And then at this point, we invoked the concept of opening voltage-gated sodium channels. Well, we can depict this, or that idea over here, as in addition to these purple potassium leak channels, there are these transmembrane proteins called sodium channels. Now, in contrast to these potassium leak channels, which are always open, these sodium channels have a gate on them. And again, let's emphasize that the concentration of sodium on the outside is in the neighborhood of 130 to 140 millimolar. And the concentration of sodium on the inside of the cell is in the neighborhood of about 10 millimolar. So there's a considerable gradient acting on the sodium. There's a 13 to 14-fold disparity in the concentration of the sodium on the outside and on the inside. And what's more is because of the resting membrane potential being negative, there are these negative charges all along the cytoplasmic side of the membrane. The inside here is negative with respect to the outside. So now there are two forces that are effectively driving the sodium into the cell. The first is a concentration gradient. There's this concentration gradient, 130 versus 10, but there's also an electrical gradient. So there are multiple forces driving the sodium from the extracellular environment into the intracellular environment. But what's different about these sodium channels from the leak channels makes all the difference in the world. Because these channels are gated. Under these normal circumstances at rest, where the resting membrane potential is down around minus 70 millivolts, under those circumstances, all of these gates are closed. What that means then is sodium is trying to come in. But it can't get through because that channel's closed. So again, we can think about this in terms of permeability. Under these circumstances, where we only have open potassium channels, what's the dominant permeability? Potassium. So that says the membrane potential will seek the equilibrium potential for the ions. Permeability is dominant. The membrane potential is going to be pretty close to the equilibrium potential for potassium. The reason it's not closer to the equilibrium potential for sodium is these sodium channels are closed. Now magically we're going to open them. And when these channels open, now maybe 1,000 times as many sodium channels will be open as potassium leak channels. So now the predominant permeability is to sodium. We now have open pathways across the membrane such that now sodium can easily come down its concentration and electrical gradients and come into the cell. Now over here, what we're going to describe is a change, a delta, in voltage. Such that at this point, when we open the voltage-gated sodium channels, the membrane potential will immediately go up to the equilibrium potential for sodium. Now, we placed a caveat on that last time, and I'll try to reemphasize that. And that is that it requires multiple sodium channel openings to provide sufficient depolarization to reach this magical point here, which we're going to call threshold. Now, typically, threshold's about minus 55 millivolts. We can define threshold as the potential, I should say membrane potential. The membrane potential at which sodium influx is precisely balanced by potassium efflux. Now, the only potassium channel we have available here is potassium efflux through the potassium leak channels. Now, it's an exaggeration because the opening of individual channels makes an imperceptibly small change in the membrane potential. But we can imagine here opening small numbers of these channels, and each time we open a few of them, we depolarize the membrane. So another way of thinking about this is each time we open a few of the channels, we increase the membrane permeability to sodium. But at this point here, at threshold, the tendency for sodium to come in is precisely balanced by the tendency of potassium to go out. And you're on a teeter-totter. The slightest change in sodium influx, and you build up positive charge such that at this point, all sodium channels open. So now there's an explosive opening of all the sodium channels because you've exceeded the amount of positive charge that can be carried out through the leak channels. You build up that positive charge will then lead to the opening of all these gates, permeability to sodium skyrockets, and the membrane potential depolarizes toward the equilibrium potential for sodium. And where we left it last time was that if we would open these sodium channels simultaneously, and that's all we did, we just had the sodium channels open, the membrane potential would then be up around plus 40 millivolts, it'd be someplace up here near the equilibrium potential for sodium. And because there were so many more sodium channels open than the potassium leak channels, that would now be a new equilibrium potential, would be stable there. But that doesn't happen, and the reason it doesn't happen is that shortly after these channels open, they close. So two things I want to emphasize here. And I'll go into some detail on this more than I'll really require you to know. But now across the membrane here will be alpha helices. Each sodium channel contains 24 alpha helical regions. 4 of these alpha helical regions, 4 of which are called S4 regions. So placed in the channel placed in the transmembrane protein around the channel are these 4 alpha helical regions. Now, what's interesting about the 4 alpha helical regions is that they have R groups on them, and that these R groups are charged. So they may be positively charged. So let me label this as positively charged R groups. Now, normally, when the inside of the membrane is negatively charged, they're interacting with neighboring alpha helices. Because remember, there are 24 of them. We'll see, in fact, that there are 4 sets of 6 nearly identical transmembrane regions. So this S4 region is interacting with its neighboring alpha helices. It's in a low order state because positive charge on the S4 will be interacting with negative charges on neighboring alpha helical regions. But now we make the inside of the membrane slightly positively charged. We'll see a little later that this normally will happen by open ligand-gated channels, but right now I just want you to recognize we're going to change the distribution of charge just by a little bit. So we depolarize the membrane. When we depolarize the membrane, the interaction of these 2 alpha helical regions, the S4 with its neighbors, becomes a little bit unstable. And the alpha helix, the S4 region, will now pop up just a little bit. It's repelled by the positive charge. The positive charges on its R groups are repelled and it pops. Now, there are 4 of these S4 regions around the channel. If 3 of these S4 regions pop just by this little bit, they literally tug on the gate. It's as though you can envision a gate in a field and you have a chain or a rope on that gate, and when these S4 regions pop, they tug on the gate and open the channel. The tugging on the gate, opening the channel, now provides a pathway for sodium to come rushing into those cells. That provides positive charge. That positive charge then tells the neighboring S4 regions, pop out of the membrane, pull on the gate, and let these channels open. And if there is enough sodium coming in through each individual channel, so each channel is carrying a little bit of positive charge, if we could get enough aggregate positive charge in the neighborhood, then everybody opens simultaneously. We have reached threshold, and we drive the membrane potential, the equilibrium potential for sodium. Yes? So the S4 region, now envision the S4 region as the spiral staircase, right? And as you go around those steps up the spiral staircase, remember there could be as many as 40 of these, maybe a few more going across the membrane. Some of those steps have positive charges on them, and they will be interacting, those positive charges will be interacting with negative charges on steps of neighboring spiral staircases. Then when the positive charge comes in, it literally moves the spiral staircase up just a little bit, so that now it has another set of charges in R groups that come to a new stable state with their neighbors. But it moves by a few angstroms. And when the S4 region moves by just a little bit, and you get all 3 or 4 of them working in concert, they can provide enough force to pull open the gate. And it's the movement of the S4s with relationship to their neighbors and coming to a new low order state, so their positive charges are in a new low order state with the negative charges in their neighbors, that allows for the movement and also allows for the tugging on the channel, or tugging on the gate, I mean. Okay? Anything else? Yes?
Was it the sodium coming in that was doing that, or the sodium that's in the positive charge?
So the question here is, what's causing the S4 to move? What's causing the S4 to move is any positive charge in here. Normally, that increase in positive charge is going to be sodium in almost all cases, because that's usually the positive charge carrier coming in. Yes?
So not like all the R groups on the alphabet like more region positive.
No, okay, let's be a little careful here. So remember that these R groups on the S4 are buried with their neighbors of other alpha helical regions. And this positive charge is not going to directly change the charge on the R group. All it's going to do is, just as when you take two south poles of a magnet and bring them close together, they start to repel. This positive charge on the sodium will cause the positive charges on the alpha helix to be repelled away from that positive charge. And as they're repelled, then they move just a little bit and they come to a more comfortable position with neighboring negative charges. But because of the movement, because the S4's popped just a little bit, and it requires several of them to pop simultaneously, we open the channel. But we don't need this positive charge to affect the long-term positive charge on the R groups. It just moves them. Anything else? Yes?
When you say the S4 region pops, do you mean like it extends or it moves completely?
So the question here is, what do I mean by popping the S4? And I want to be careful here. It actually will not change the distance between each of the amino acids. The whole thing pops. The entire structure moves. I think what I'm a little concerned about is you're thinking about pulling out the alpha helix, basically stretching it like we talked about elastin and pulling it apart. No, it doesn't do that. The whole thing remains with its relative hydrogen bonding along the backbone of the alpha helix. That doesn't change. So the distance between neighboring amino acids doesn't change. But the relationship of the amino acids with their neighbors around neighboring alpha helices does change, and it moves up. It literally moves. Not very much, but enough that when three of them open, they can pull the channel open. So now we've opened the channel. So we've talked about the S4 playing a really important role in opening the channel, but now down here in the cytoplasm is a region, and I'm going to, on each one of these, I'm going to label this as the ball and chain. There was a time not so long ago when we actually envisioned it this way. We thought there were a long string of amino acids down here that provided a ball and chain, and when the gate opened, it would move up into the mouth of the channel. If you envision it that way, if you can hold on to it that way, that's fine. In reality, there are only 3 or 4 amino acids on the cytoplasmic side that have to move in position, and they will inactivate the channel. But conceptually, if you imagine there's something down here on the cytoplasmic side of the protein, so that after the gates open, within a matter of a fraction of a millisecond, something changes to the cytoplasmic side that you basically block the channel. That will do. So we can say that the ball and chain inactivates the sodium channel, And in some places, you'll see this ball and chain referred to as the inactivation gate. Regardless of what we call it, what it's saying is we now get a configurational change down here so that we basically plug the channel. When these channels are inactivated, they are effectively closed. So up here at the peak of the action potential, at this point, these ball and chains are moving into the open channels, inactivating them. You can think of them as being turned off. And where we left last time was to emphasize that if all we did was open these voltage-gated sodium channels and didn't invoke any other channels, that over time, the membrane potential would slowly return back down toward the equilibrium potential for potassium. And that would occur simply by invoking this relatively small number of leak channels, because positive charge will leak out of the membrane through these channels. But in fact, that's not what happens in biology. In fact, in biology, the membrane potential now repolarizes very rapidly. So this is said to be the repolarization of the membrane potential toward the equilibrium potential for potassium. So we're going to repolarize the membrane potential toward the equilibrium potential for potassium by opening voltage-gated potassium channels. So let me make some room here and continue the structure of this plasma membrane out a little bit. So again, some phospholipid bilayer. But now across the membrane is going to be this transmembrane protein, which we're going to label as a voltage-gated potassium channel. In contrast to the purple leak channel, this channel actually has a gate on it. And as the name implies, it's charge sensitive. So we can open the gate on this channel with charge. Yes?
Actually, the question going back to the ball and chain was, so is that, when it closes, is that how it was originally shut when the channel was closed, or does it have a different means of being closed now?
Okay, something I wanted to skate by. So the question here is, what is the relationship between the ball and chain and the gate? They are different parts of the molecule. And the ball and chain is just a few amino acids which are necessary to move into the site to close the channel, to activate the channel. And why we call this an activation gate and we call this an activation gate is because they're separate parts of the protein. So the gate is one piece of the protein and the activation gate is another. And so we open the gate, and one of the things you're pointing toward is an important concept in biophysics, is that once we open this channel and allow the ball and chain to move back in again, even though the channel is inactivated, it doesn't come back to an openable state until we repolarize the membrane and reset the part of the protein, which is mostly the S4s and the gate. Yes? So the question here is, what causes the ball and chain to move into its place? That seems to be completely stochastic thermodynamics. I mean, it's thermal effect. It's the vibration of the protein. And there doesn't seem to be any other mechanism other than time and the stochastic probability of this thing popping into the channel. Now, the probabilities are pretty high that it's going to pop into the channel and are high enough that you can inactivate all these sodium channels within a fraction of a millisecond. But it appears to be dependent entirely upon time and the random event of it inactivating the channel. Yes?
So when the sodium channels open, there's some kind of pressure created inside the cell, right? And however small. Potassium then has to leave the cell, right?
Okay, so let's see if I can explain this, because this is an important question. The question is, what drives the sodium in through these channels? You named a pressure. Well, there are two pressures driving the sodium in. One is the disparity in charge. It's more negative on the inside than the outside. That's the electrical gradient. But there's effectively another pressure driving the ions in, and that's the random walk of the sodium. But there's so many more there's so many more sodium ions out here than inside that the pressure is for the sodium to move down its concentration gradient. So you're right. There are two pressures, one which we call an electrical gradient and the other we call a chemical gradient, moving these ions into the cell. Okay?
Absolutely, but the potassium's got to go somewhere, right?
So where's the potassium go? Okay.
Well, I figured it was pushed out the leak channel.
So the potassium will move out of the leak channels. But this is an important concept that we really need to drive home here. And I don't want people to get sort of mixed in it. And that is that when the sodium comes in, the concentration of sodium, the sodium concentration with this change and excursion of the membrane potential, the sodium concentration on the inside goes from 10.0001, 0 millimolar, to 10.0001 millimolar. So we hardly change the concentration at all. And that's what you're recognizing. So we hardly change the concentration at all, but now that leaves only one gradient for one ion to allow for the positive charge to leave. The only charge carrier we have that can move down its concentration gradient is potassium. The only route through which it can move is through the leak channel at this point. And the pressure driving it is the disparity in concentration, and to some extent the large negative anions, because they're going to be also, and to some extent, right, it's almost all that. Let me rephrase that. Almost all of that is the concentration gradient, allowing them to leave. So anything else before we go on to the next channel? So in red here we have voltage-gated potassium channel. These voltage-gated potassium channels have another name, and I really like this name because it describes what they do. They're called the delayed rectifier. Now, if you take another physiology course, you're going to find that there are a whole gang of different potassium channels. There are several genes for potassium channels, and they're ultimately spliced, and there are a whole bunch of them. But for our purposes, the one we want to talk about here is the one that is voltage-gated, and it's the delayed rectifier. The name has an implication to it. It's delayed in time, but it's a rectifier because it's going to rectify the membrane potential. So it's delayed in time. It only comes on, it only opens after the voltage-gated sodium channels have opened. So you have a delay in time, then the potassium channels open, but now because of the gradient and because of the permeability to potassium, they will rectify the membrane potential, driving it back down toward the equilibrium potential for potassium. Yes?
So what you're saying is that mechanism just makes the repolarization or the repolarization of potassium faster?
So am I saying that what we're talking about here is the opening of these delayed rectifier channels, the voltage-gated potassium channels, just makes the repolarization faster? Absolutely. It's just a mechanism whereby we can increase the permeability of potassium a whole bunch really fast. Yes?
So it's the sodium then that triggers the opening of the voltage-gated potassium channels, but it's just slower.
So the question here is it the sodium that triggers the sodium being the charge carrier for positive charge that triggers the opening of the voltage-gated potassium channels? The answer is yes. And the only difference between triggering the opening of the voltage-gated sodium channels and potassium channels by positive charge is time. Yes. Okay. Let me go through a couple of slides here. And give me a moment to see if I can rummage around in my pack here and find the other. Laser pointer. Okay. So this is just describing the membrane potential. So potassium is leaving down its concentration gradient, is rapidly held in check by the large negative anions to generate the resting membrane potential, the equilibrium potential for potassium. These channels are meant to represent the voltage-gated sodium channels. They look like teeth, but we know exactly what the amino acid sequence is. We know their structure down to exquisite detail. But for our purposes here today, all we have to know is that there's a gate on these channels. That gate is normally closed, but this gate can be opened by an increase in local positive charge. We'll see a little later that positive charge largely in biology will result from positive charge coming through ligand-gated channels. That is, neurotransmitter-gated channels will open and allow positive charge to come in, and that will be the genesis of this increase in positive charge. That positive charge opens the gate. We describe the S4 regions, which move and pop open the gate by pulling on it literally. When we open the gate, sodium can come in, but it only comes in briefly before the ball and chain pops into the mouth of the channel, the cytoplasmic mouth of the channel, and stops the flow of sodium ions. You close those sodium ion channels. The next image is for the voltage-gated potassium channels, and they look pretty much the same. What you see again is a gate. The gate is opened by positive charge, and what's missing here is an inactivation gate. These guys don't inactivate. The delayed rectifier doesn't have a ball and chain. So once it opens, ions now leave down the concentration gradient. And these channels then will close once the inside of the membrane becomes negative. But again, what's different is not the mechanism of opening the channel, because after all, both the sodium and the potassium channels open in response to an increase in positive charge. What's different between the two is just the timing of the opening. The delayed rectifier is slower to open. So let's look now at the next figure. And if you can walk your way through this figure and explain all aspects of it, you understand the action potential. So let's walk through it piece by piece. First, we're going to start here. We're going to say, there's the resting membrane potential. Now, the resting membrane potential, they've set at minus 60 millivolts, and you'll notice that's slightly more positive than the equilibrium potential for potassium. Now, in our thought experiments, we have said the resting membrane potential is determined by the potassium equilibrium potential. They're all the same. It's not quite true. The reason it's not quite true is that the sodium channels, these voltage-gated sodium channels shown in green, are always flickering open and closed. So they're always providing a certain low level of membrane permeability to sodium. Remember, the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Well, the dominant permeability down here, because we're so close to the potassium equilibrium potential, that dominant permeability is potassium. But there is a little bit of resting sodium permeability. So that makes the membrane potential, the resting membrane potential, just a little more positive than the equilibrium potential potassium. They're showing here minus 60. So that's the resting membrane potential. But here in green, the green represents the open voltage-gated sodium channels. The black represents voltage. So as we start to open these green voltage-gated sodium channels, we depolarize the membrane. As we open more and more of these green voltage-gated sodium channels, we more and more depolarize the membrane potential until we reach something in the neighborhood of plus 40 millivolts. Then, as we reach the peak of the number of open voltage-gated sodium channels, they inactivate. They close. At that point, and watch the red line here, the red line is depicting the number of open potassium channels. These are the delayed rectifier channels. And so there's delay in time, and these guys start to open. And so they open, and they now begin to repolarize the membrane, such that now the dominant permeability is to potassium. Now let's follow this completely out by following the membrane potential. Here we depolarize the membrane potential. We make it more positive by the opening of the voltage-gated sodium channels. Near the peak, the voltage-gated sodium channels are inactivating or closing. But now, just about this time, we begin to see an increased opening of the delayed rectifier. Again, they're delayed rectifiers. They're delayed in time, so it takes them a little longer to open. So they open, and as they open, the dominant permeability now becomes to potassium, because these sodium channels are closing. They're inactivating. Now, let's follow the potential. We depolarize to plus 40, and now we repolarize the membrane. And now at this point, it approaches the equilibrium potential of potassium. So why is that? How do we explain the membrane potential approaching the equilibrium potential of potassium at this point? It is a hyperpolarization, fair enough, but it's not a hyperpolarization below the equilibrium potential of potassium. It approaches the equilibrium potential of potassium. We can't get lower than the equilibrium potential of potassium only using potassium channels. But we approach it for two reasons. One is the delayed rectifier channels are open. But in addition, so now we have more open potassium channels than we had at rest, because at rest we only had the leak channels. So now we add on top of that the voltage-gated potassium channels. So we add on top of the resting permeability to potassium, the permeability through the voltage-gated potassium channels. What's more is these green sodium channels are inactive. They've been inactivated. So they're not available to flicker open. So they can't provide any depolarization. So that's why the membrane potential during the so-called undershoot phase comes precious close to the equilibrium potential for potassium, because we've taken the sodium channels out of the story and we've added more permeability by opening the voltage-gated potassium channels. If you can walk your way through this series of events and understand what's happening to the permeability at each point and what's happening to the corresponding change in voltage at each point, then you have a good grasp of the action potential. So any questions to that point? Yes?
I mean, it looks like you're going to go there, but there has to be some kind of capacitance there, right? In order to.
Oh, you want to invoke capacitance. Let's do that later. All right. We will. And you're absolutely right that the truth of the matter is that this phospholipid bilayer is a tremendous capacitor. This is a dielectric which effectively separates charge. And at rest, there's a capacitance between the negative charge inside and the positive charge on the outside. And the truth of the matter is, to get really good flow of ions through these channels, you have to first offset the capacitance. But let's hold that at bay. I'll be happy if you get ions moving through channels for now, and we'll come back to the capacitance a little later. But first, before we do that, there's a point I want to make here. First is that influx of sodium hardly changes the concentration, but has an enormous effect on charge. That's true for the other direction too, that when the potassium flows out, when potassium goes out through the potassium leak channels, when the blue potassium goes out through the potassium leak channels, we can repolarize the membrane potential back down to rest by changing the cytoplasmic concentration of potassium from about 110 millimolar to about 109.9999 millimolar. The importance of this is to recognize that we can shift the electrical potential across that exquisitely thin membrane by a whole lot. The excursion here is typically 110 millivolts. So we change the potential a whole lot without hardly at all affecting the concentration. Now you're right. If you look at this for a moment, you say, well, what happens if there are thousands of these action potentials? Over time, you will change the concentration gradients. And at that point, you have to invoke the pump. You have to invoke a pump which is going to pump the sodium out and the potassium back in again. But that pump is slow. And I imagine that pump being a lot like your cell phone battery. And you know full well that you do have to recharge your cell phone battery now and again, but you can send a whole lot of texts before you have to recharge it. And you have a question. Okay, so let me finish with one drawing so that we're in the same position as the other section. And in this drawing, what I'm going to do, let's do it this way. So this is our pineapple neuron. This is our cell body. This is our axon. Now, in this thought experiment, all along the axon, we're going to put in these potassium leak channels. And in this thought experiment, we're going to cluster the voltage-gated sodium and their counterparts, the voltage-gated potassium channels. Only at this site. Now, we can imagine out here, their synapses, they're going to deliver positive charge. They'll open these channels, and if we draw the membrane potential change, we start at -70. And it goes up to +40. And then it repolarizes. What I want you to think about between now and tomorrow is what happens to all of this positive charge which has come into the cell through the voltage-gated sodium channels, what happens to it with respect to these potassium leak channels, and how will this amplitude of minus 70 to plus 40 change as we move along the membrane, as we propagate along the membrane with only leak channels, and we'll describe that tomorrow.